So now that we have our simulation of the runaround loop working, we can use it to do some parametric studies. So there's all different kinds of things that we could do. We could design the components or whatever. But what I'm going to do here as a parametric study is just optimize how we operate the runaround loop. So let's see. In this case, all I'm going to do is optimize the pump speed. So I'll set the ethylene glycol concentration to a high enough value that we won't freeze even on a very cold day. But I can potentially optimize the pump speed. So if I'm going to change the pump speed, one thing I have to be cognizant of is that up here, the guess values and the limits that I set for my volumetric flow rate, which is one of those iteration variables, may not be appropriate. So if I reduce the pump speed, for example, this guess value could be outside of what the pump speed could do, or perhaps this upper value isn't high enough if I increase the pump speed. So what I'm going to do down here is create a variable. So this will be v dot displacement, and this is just going to be the displacement of the pump. So that would be what would that be? That would be the pump displacement, the pump speed, multiplied by the pump's displacement. So that's the displacement rate of the pump. That's the maximum flow rate that the pump can give. So I'm going to use that up here as my upper limit. So v dot displacement. And then the guess would be something between 0 and this pump speed. So let's make v dot guess, I guess. And let's set that to 90% of the displacement. So when I'm searching for a solution, that's where my search is going to start. So v dot guess. So it should still solve, I hope. Yep. And I should set the units of this new variable. This is meters cubed per second. And this is also meters cubed per second. And everything works now. Okay, so what I'm going to do then is vary this pump speed in order to maximize some objective function. And so maybe the second thing I had to do is figure out what am I trying to maximize. Certainly I'd like to maximize the rate of heat transfer in this outdoor air coil. That is sort of the benefit of the system. The drawback of the system is that I have to run this pump and the fan, so maybe I want to have an objective function that includes all of those things. So right here I'm going to do objective equals q dot OC, and then I'd want to subtract from that some multiple or something, some constant times the pump speed. So maybe I decide that electricity is worth 3 times as much as heat transfer, so 3 times W dot pump. And I could include in here 3 times W dot fan if I wanted to. So ICB minus 3 times W dot, what's it called? OCB, I think it is. Yeah, OCB. So this is some objective that accounts for the fact that I want energy recovery, but I'd really rather not have electricity consumption. So let's make sure that looks okay. This should have units of watts. It does. The energy recovery was 542.2 watts, and then I subtracted from that 3 times all of the electricity recovery, most of which was this pump, 14.44 watts. Alright, so that's good. I guess now this is my independent parameter to carry out my optimization with. So I'll comment out this independent parameter, and I'll come up here and select not solve anymore, but min max. And my over here I'm going to set the objective. I want to maximize the objective, and then over here the independent parameter is MP. And I have to set some bounds. I don't know, let's go between 5 and 40, something like that, and hit apply. Okay. I have to set the method. Maybe try with golden section search to begin with, and we'll hit OK. And now it's going to go try to do that optimization, and it should find a solution. and that's the solution. It's decided that 17, what is it here? 17.95 is the pump speed that maximizes that objective function. If I want to look at it more carefully, I can make a parametric table. So let's do that maybe real quick. Parametric table that includes, let's see, the pump speed, certainly the objective function. Where's that? Right here. And then the different things that make up the objective function, which are primarily Q.OC and W.pump. And let's run the pump speed all the way from 5 to 40 and hit OK, and then we'll run this parametric table. And I think what you see here is as the pump speed increases, your energy recovery first increases and then actually decreases, but your this right here, this is the energy recovery. Actually, let's just plot this. So new plot. We'll plot the objective, and so all three of these. If I hold down shift, I can get all three of them. And there's my plot. So yeah, this blue line is the energy recovery. It actually starts to come down as your pump speed goes up. This red line just goes up. This is your pump power. And then the blue line minus the red line is your objective, and that definitely has an optimal value where you're getting most of your energy recovery but not too much pump penalty. So that's interesting. Maybe one more thing we can do is look at how we might want to change how we control the pump speed as a function of outdoor air temperature. So what I can do then is do min-max table. So I'm going to comment out the outdoor air temperature as well. I'm going to build a new table that includes, let's see, let's include the same thing. So I definitely have to include my objective function. I have to include this parameter that I want to change, so that's T outdoor. And I have to include my independent parameter, which is MP. That's what I want to actually optimize in each run. Now I can include other things if I want, so I included W.P. I might also want to include Q.OC, whatever that is right here. And I think that's good. And then I am going to run my study from, I don't know, let's say minus 20 degrees Fahrenheit to 20 degrees Fahrenheit. That should be a pretty good range. And if I do min-max table now here and calculate, I see that what I'm going to do is maximize the, so it's only picking stuff out of the table now, right? I'm going to maximize the objective function, and I'm going to vary the pump speed to do that. And because I just solved this problem for 20 Fahrenheit, I probably want to start at the end of the table and work my way to the front. It'll just probably converge better, so I'm going to solve in reverse order. We'll stick with golden section search and hit OK. And now it's going to start doing an optimization for every run of this table. So you can see it just got done with run 10, and now it's doing run 9, run 8. This is going to take a little bit of time. So it's done. You can see it's got a solution here for every value of outdoor air temperature. Now again, it can maybe be instructive to plot this. So let's make a plot of, let's see, the objective function is a function of the outdoor air temperature. And yeah, that's probably good. Let's maybe also put the pump speed on there just for, let's put the objective function in the pump speed. Actually, why not put everything on there? So we'll put OK. And there's our plot. Maybe we want to put a couple of these on a secondary axis. So those two in particular probably should go on their own axis. So let's put NP on its own axis. And yeah, I think this is probably good. So here we have the same kind of situation where we have the green line is the objective function. I'm sorry, no, the green line is the energy recovery. Obviously, I guess the energy recovery is better as it gets colder outside. A bigger temperature difference between your house or the building and the outside air. The blue line here is the pump's power, which doesn't really change very much, and you can see that more clearly if you look at the pump speed on the secondary axis, which is changing but not very much. And so there's an offset between the energy recovery, which is the green line, and the objective function, which is the black line. But yeah, that's an interesting study that is only possible because we have a fairly detailed model of the runaround loop and how it works.